about comparison tests. Let's go back and look at comparison tests, and then we saw an example where a comparison test wasn't too useful. And so we're going to talk about two more tests, the ratio test and root test. Has anybody looked at web work and need any help with web work before I get started? Yes, sir. Okay.
1 over x times the ln of x all squared.
And is that a series or an interval?
It was an interval.
It was an interval, then you want to decide on the series? Okay, so we want to compare, see what this does. And it's just the natural log is squared, correct?
It's the x ln of x. Oh, yeah, just the natural log.
Like this?
Yes.
And I suppose we're going from 2 to infinity.
Yes.
We're going to see what this integral does to help us make a decision on what this series does. Remember in the integral test that the integral does whatever the series does. So, do we need some help integrating this thing? It is a u du integral. U is going to be the logarithm. I'm going to move over. That's not going to move over. Okay, I hate doing this. So we're going to take u to be the stuff in the parentheses, because the derivative of that will give us the 1 over x. So we've got a 1 over u squared times du integral. We integrate that as u to the negative 2 and use the power rule. We'll add 1 to the power and divide by the new power. And so we get u to the negative 1 divided by negative 1. And u is the natural log of x. I'm going to write u to the negative 1 as 1 over u. And now I'm going to put the natural log of x in there. We need to take this from 2 to infinity. So here's where I'll make it a limit. As n goes to infinity, and then evaluate this from 2 to n. So I've got negative 1 over the natural log of n minus a negative 1 over the natural log of 2. In that first term, the log of n is in the denominator. So as n gets large, so does the log of n. And then we use the fact that 1 over infinity essentially is 0, or limit, it is 0. So this term becomes 0, and this is a constant. So the integral has a finite value. Since the integral converges, so does the series. Now let me show you another way to check that this series converges. Logarithms we can use in integral tests, but also in comparison tests. So let me show you another way. Let's look at a comparison test. I don't know if I'm going to use the direct comparison or the limit comparison just yet, but I think it's going to be the direct comparison. Remember, in a comparison test, you pick a series that mimics the behavior of a given series real closely. And then if we know the behavior of our comparison series, how it compares in size to this one makes our decision known, right? We have that if our series is smaller than a convergent series in direct comparison, then our series converges. If our series is bigger than a divergent series in direct comparison, then our series will diverge. So I'm going to compare, these are the AKs, 1 over k, natural log of k squared. And I'm going to compare it to this series. Because in our tower of power, one of the things that's larger than the natural log of k, but is real close to the natural log of k, is the square root of k. Think about their graphs. The logarithm looks like that, passing through 1, 0. The square root function looks like that, but it passes through 0, 1. And the square root function's a little bit larger. Now, when I simplify my bk term, I get 1 over k squared. So the series 1 over k squared is a known one. That's a p series. The value of p here is 2. What does that tell you about whether this converges or not? P series bigger than 1 converges, P series smaller than 1 diverges. This is bigger than 1, so it converges. So now let's compare the sizes. I know that k times the natural log of k squared as a denominator is smaller than k squared because I've replaced this with the square root of k. The square root of k is bigger. And so if I do the, right, that's smaller than that. So 1 over k, natural log of k squared, is bigger than 1 over k squared. So bigger than convergent isn't one of our statements, right? Bigger than divergent would be, but not bigger than convergent. So what happens if we try, oh, the limit comparison test isn't going to work either. Sunny biscuits. Okay, so screw this idea, but let's look. So direct comparison test doesn't work. Limit comparison test is not going to work either. Let's see if I've got room to work it. I do. In the limit comparison test, we take the limit as k goes to infinity of our given series over our comparison series. And if we get a positive finite limit, both series do the same. Well, if I take this thing here, and divide it by that one, I'm going to get an infinite limit. Can you kind of see that ahead? Put that k squared up here. The k's will cancel. Maybe I'll get an infinite limit. Let's see. I might have to do L'Hopital's rule. I have infinity over infinity. So let's do L'Hopital's rule and see what that limit is. L'Hopital's rule says take the limit of the derivative of the top over the derivative of the bottom. The derivative of the bottom with the chain rule gives me that. Let's see how far I could move over here. I could move over here. So that simplifies to the limit as k goes to infinity, This k goes on top. And why is this limit infinite?
You'll keep spitting out a k on the top.
That's right. I'll always have something bigger than the log of k on top. It's bigger on top. Well, that infinity case of the limit comparison test is also for divergent series. So the limit comparison test doesn't work. So I think either I picked a bad comparison series or the integral test is probably the easiest way to go. So neither one of these tests work. Sorry, led you down the old rabbit hole. Anything else from web work? So the integral test is useful. A lot of folks stay away from it because integration takes a bit. The integral test is pretty dang useful. Yes, sir.
I was doing 8.4 and I was having trouble figuring out my BKs.
Okay.
LCT.
Okay, let's look at some more comparison tests. So, look at some more comparison examples. And this is a typical comparison to compare the natural log of k to the square root of k. So when you're making your comparison series, a lot of times that's what we'll do, is just take the natural log of k out, put the square root of k in. And many times it works. Let me find one. Like here, it would work real easily. This looks very similar to the one that we've done, except for the logarithm's on top. And there's a couple of comparison series that you can use. If you're familiar with the Q log, you remember the Q log series? We can compare this to a Q log series because it's almost one. Right there's the Q log series. Or we can compare it the way I did here. I can replace the log of k with the square root of k and compare it to a P series. So two choices for BK, and both of them are legit. Just the Q log series. That's a convergent Q log series. Remember, your Q log series behaves like a P series in that it has the P series term on the bottom and the logarithm on top. And the size of the power here tells us when it converges. If the power is bigger than 1, the Q log series converges. If the power is smaller than or equal to 1, the Q log series diverges. And this is Q is 3, bigger than 1, so it's convergent. Another choice for BK is in the P series. Replace that with the square root of k. And that simplifies. Let's see, that's a k to the 1/2. Take a half away from 3 and I get 2.5. So that's 1 over k to the 5/2. And that's a convergent P series. I think either way, we need to do the limit comparison test. Because if I choose this one, I've made the numerator smaller, kept the denominator the same. So this series is smaller than the given series. Or in other words, the given series is bigger than that one. So I can't use the direct comparison test. This one, I can use the direct comparison test. I kept the denominator the same, but I changed the size of the numerator to something slightly bigger. So this is bigger than that, and that would make that a direct comparison. So let's do the limit comparison with this one. So let me call this one number 1, and this one number 2. So number 1, we use the limit comparison test. Again, in the limit comparison test, we take the limit as k goes to infinity of the given series over our choice for comparison. And so I'm taking the limit as k goes to infinity of 1 plus the natural log of k over k cubed. My comparison was the log of k over k cubed. So in the flip and multiply step, the k cubes will cancel. And I'm just left taking the limit as k goes to infinity of 1 plus the natural log of k over the natural log of k. So here you can kind of use the tower of power where they both have the same behavior, numerator and denominator. So that limit should be 1. If you don't believe it, if you do L'Hopital's rule, you get 1 over x over 1 over x, or 1 over k over 1 over k. So L'Hopital's rule also gives us a limit of 1. In the limit comparison test, anytime you get a positive finite limit, our conclusion is both series do the same thing. This one converges, so our given series converges. Now, I said if we use choice number 2, we can do a direct comparison test. Because we have our AKs smaller than our BKs. If K is big enough, this 1's not going to mean diddly, but the natural log of K is smaller than the square root of K, and the denominators are the same. And so here we have the statement that the given series has terms that are smaller than the terms in a convergent series. Smaller than convergent is convergent. Okay. Let me try something else here. Let's see. These are all the same. They are. I'm sorry? This is all still comparison test in section 8.4. Section 8.4. So we had some questions about how do you pick the BK term? Let's look at this one. Suppose my series looks like, say, the square root of K minus the cube root of K plus 4 divided by K k squared plus k plus 1. Or even make it more interesting. Interesting. Who wants interesting? Let's leave it at that. If you have terms that are k's to a power that are added or subtracted, sometimes even multiplied, to make the bk term, all you do is throw away the lowest powers and keep only the highest power of k on top and on the bottom. So on the top here, the highest power is the square root of k, and on the bottom, the highest power is k squared. So I pick my bk just to have those two terms in it. So that's what we typically do when we have something shaped like that. We just throw away the lesser significant terms. So we pick our bk series to be the series that has the square root of k divided by k squared. Which when we simplify that, that's k to the 3/2 power on the bottom. So I simplify it to see that it's a p series. P is bigger than 1, and so it's a convergent p series. Now, when I do this exchange of just dumping terms like that on the top and on the bottom, then I typically go straight to the limit comparison test. Because I don't know how my sizes compare when I throw away more than one term. Or maybe I don't even want to work hard enough to figure it out. I think I've made something that's bigger than that because I threw away something that was subtracted. So already that's bigger than that. Threw away a 4, that's piddly when you're way up for big values of k. And I threw away terms in the denominator, so I'm dividing something bigger by something smaller, which makes this bigger. So I think with that rationale, I could do the direct comparison test. But the limit comparison test is easy when I keep the same powers, the highest powers. My limit comparison test should be real simple. So I'll go ahead and do the limit comparison from this one. Limit k goes to infinity. So I got all of this. I'm going to divide it by its unsimplified form, so it's easier to take the limit. Let's see if I can get this out of your way. I'm dividing that by bk. So I'll flip it over and multiply. Or at least I'll pretend I'm going to multiply. Do I need to multiply that out, or can you tell what the limit is? The limit is indeed 1. Both of them are going to have a k squared times the square root of k on the top and the bottom, and everything else is lower in power. So if they both have the same power, top and bottom, then the limit's just the ratio of the coefficients. Everything else is lower power. And so our limit's 1. And again, with the limit comparison test, any positive finite limit says both series do the same thing. So our series converges. because again, we had a convergent p-series. So it's important that you label it here, because when you get bogged down in these steps, you want to be able to backtrack to see what your comparison series did. So I like to compare logarithms of square root of k. When you have things that behave kind of like a polynomial, I just throw away the lower power terms. If we have geometric series type terms in there, I try to keep those, keep the fastest growing terms in making the comparison. Did you have one in particular that you wanted me to look at? Or does any of this help?
It was one like that with polynomial.
What's your thought on this one? We can start at 1, I guess. Absolute value of the sine of k divided by k to the 4th plus 2k. Sine of k plus absolute value of the sine of k divided by k to the 4th plus 2k. What would you compare this to?
I don't know what you
How big is the sine going to be in absolute value? How big? Between 1 and 0, it's an absolute value. So the very largest, the numerator of this will be is 1. And the largest thing going on in the denominator is k to the 4th. So we know that sine of k in absolute value is always going to be no bigger than 1. So we're going to compare this to we'll put a 1 up here and a k to the 4th here. So I made the numerator as large as possible. So this is always bigger than that. Then I took a positive term away from the denominator. So I've got a larger over a smaller. So how does this fraction behave in size compared to that one? It's larger. So we have 1 over k to the 4th is larger than the sine of k over k to the 4th plus 2k. This is a p-series. That is a convergent p-series. So I can use a direct comparison test because this says that our series has terms that are smaller than the terms in a convergent series. Smaller than convergent is convergent. That's the direct comparison test. So sometimes if the sizes are obvious, then don't do the limit comparison test. Just do the direct comparison test. So with practice, you'll see which ones, how to compare a little bit better. In your web work, there's one problem that has a set of choices to compare to in all the problems. A 1 over k, a 1 over k squared, a 1 over k to the 3/2, and things like that. So you pick the best one and it kind of guides you through the problem. But the overlying thing here is that you've got a lot of times things that are added. P-series type terms added to each other, geometric series type terms added to each other, or subtracted. And those lend themselves well to comparison tests. The ratio test and the root test lend itself better to things that are products. Did we do enough examples on the ratio and the root test? Did we do any? None? Then let's start from there if you have no more questions. Okay, so 8.5, the ratio and the root test. It's not working for me so well. So this again is a positive term series test. All the terms are positive. But you'll see in the next section that it also works in absolute value. So it's a really handy dandy, easy test to use. So for the positive term series, again, what that means is we're adding a bunch of stuff together so that when we're out here somewhere, we've got the kth term, the k plus first term, and then we keep on adding. In order for this series to converge, we said a necessary condition for convergence was that these terms eventually go to 0. But that's not a sufficient term. We need them to go to 0, but we need to go to 0 fast enough so that that sum stabilizes out. One way to tell if the terms are going to 0 fast enough is to look at the ratio of consecutive terms and look at their limiting behavior. And that's what the ratio test does. Suppose you take the limit as k goes to infinity of the k plus first term over the kth term. And you get some number L. Well, if L is equal to 1, then that really provides little to no information. If L is equal to 1, it says that the long-term behavior of k plus 1 terms is very similar to the long-term behavior of k. And we don't know. They behave like each other, but who cares? So are they behaving in the good way, in that they're both going to 0, or are they behaving in the bad way, where they're both getting bigger? So if L is 1, that's not good news. This test provides no information. But it does provide information if L is smaller than or bigger than 1. If L is smaller than 1, so think of a fraction over here, smaller than 1, and I put this term up here, that says that my subsequent terms are a smaller fraction of the previous terms, or my next term gets smaller by a fractional amount than the previous term. So if these are small enough to begin with, then a fractional amount of that is even smaller. So it is going to 0 fast enough. So if this limit is smaller than 1, our conclusion is that this series converges. It's essentially the same statement as saying smaller than convergent is convergent, because these guys down here would be smaller than these things here. If L is bigger than 1, then if I do that cross multiplying thing, maybe assume the limit over here is 3 or something. And then if I multiply that, it says AK plus 1 is 3 times AK, which means this is 3 times bigger than that, or getting bigger. And we don't want that. If L is bigger than 1, the series diverges. The only problem is if L is equal to 1, you don't know anything. The series isn't, this test isn't applicable. This test is inconclusive. Try something else. Usually a ratio test or I'm sorry, usually a limit comparison or a comparison test will do it. Now, this is a ratio, and we want to be able to simplify the ratio enough to get a limit. And things that simplify the ratio are things in a product or exponents. Exponents represent products. So you're going to use this when you have lots of powers and lots of things multiplied together. Things that don't cancel are things in a sum. I can't cancel an x plus 4 with an x plus 2. They're different, right? I can't cancel through a sum. So we're going to try to use this when we have things that look like they're products. Or, let's see. Let's see, here's an example. Test the series. K is equal to 1 to infinity of k squared divided by 2 to the k. So if it weren't for that k squared term up there, it would behave like a geometric series. So it looks like it's behaving like a geometric series. I'm tempted to think that this is going to converge. But I'm going to show you how to use this ratio test to show that it converges. So all we do is set up this limit right here. So by the ratio test. We take a limit. As k goes to infinity of the k plus first term over the kth term. To get the k plus first term, you take each k and replace it with k plus 1. So k plus 1 looks like k plus 1 all squared divided by 2 raised to the k plus 1 power. Then we take that and divide it by the kth term. All right, so to divide, we're going to take this fraction here, flip it over and multiply. But I'm going to rewrite 2 to the k plus 1 using the properties of exponents. I'm going to write 2 to the k plus 1 as 2 to the k times 2 to the 1. Because remember, when you multiply like bases, you add the exponents. We'll leave this in factored form. I'm going to write that as 2 to the k times 2 to the 1. And then I'm going to flip and multiply with the 2 to the k up here and the k squared here. So really only one term cancels, but it's the biggie, the 2 to the k. And then I'm going to look at the limit of what's left. And what's left on top is just the k plus 1 all squared. And what's left on the bottom is a 2k squared. Does anybody know the limit of that stuff that's left? 1/2. Both the k squared, top and bottom. coefficient of k squared on top is a 1. The coefficient of k squared on the bottom is a 2. So my limit is a half. That puts us here. So by the ratio test, the series converges. So 1/2 is smaller than 1, so this series converges. I think the one that we ended class with last time looked similar to this, but maybe I had a square root of k over 2 to the k. So the steps would be the same. This squared would be replaced by a square root sign. And so I'd have a square root sign here and a square root sign here, but I'd still get a limit of 1/2. So the one we ended class with works just like that. What told me it was a good candidate for a ratio test was a k power, because I know I can cancel things the way I did here. Another thing that gives me a big hint that a ratio test will work well for me is when my series have terms with factorials on them. A factorial represents a product. What does 5 factorial mean if I wrote that number on the board? 5 factorial. It's the product of 5 with all the integers, positive integers down to 1. 5 times 4 times 3 times 2 times 1. So k factorial means k times k minus 1 times k minus 2 until I run out of integers and finally multiply by 1. So it's a product. That's a big clue that a ratio test will be a good choice here. So let's try testing this with the ratio test. I'll tell you what I'm going to do. I'm going to take the limit as k goes to infinity of the k plus first term divided by the kth term. To get the k plus first term's expression, just take each k and replace them with k plus 1. So in our problem, we'll have k plus 1 times 5 raised to the k plus 1 divided by the quantity k plus 1 factorial. The k plus first term, the kth term is looking at you, so we'll put it here. The next step is doing the division. Put this up here upside down. Let's also rewrite 5 to the k plus 1 as 5 to the k times 5 to the 1. on me. Oh, that guy. Let's try this one. So I got k plus 1, 5 to the k times 5 to the 1, k plus 1 factorial, flip that over, puts a k factorial here, and a k times 5 to the k here. That shows you that the 5 to the k's will cancel. Now let's look at how we can cancel here. There's k factorial. What does k plus 1 factorial look like?
K times k minus 1.
I'll have my k plus 1 term here. Then I go one integer smaller, which gives me a k. And then that gives me all the rest of these guys. So k plus 1 factorial is k factorial multiplied by k plus 1. So I'm going to replace k plus 1 factorial with k plus 1 times k factorial. I'll go ahead and cancel the 5 to the k's. K plus 1 factorial is the same as k plus 1 times k factorial. So for instance, k plus 3 factorial would be k plus 3 times k plus 2 times k plus 1 times k factorial. All right, so the k factorials cancel and the k plus 1s cancel. And all we're left with now to take the limit is 5 over k. What's that limit? 0. We compare it in size to 1, and it's smaller than 1. So the series converges. Okay, the series converges if you get a ratio test limit smaller than 1. Okay, so let's go wacky with some factorials here. This is the series 2k factorial divided by k factorial squared. Again, the giveaway that a ratio test will work well is all these factorials. All we can do is carefully set up that limit and carefully cancel. Tell myself I'm doing the ratio test. Tell myself what I'm going to do to it. Take k plus 1 and divide it by ak. And now I'm going to do it. So again, the k plus first term is found by replacing each k by k plus 1. So I'm going to have to take k plus 1, then multiply it by 2, then take the factorial. So 2 times k plus 1, then the factorial. I want you to think of k factorial squared as k factorial times k factorial. So that the k plus first term would have a k plus 1 factorial here and another k plus 1 factorial there. So that's what my k plus first term looks like in this very faint color blue. Let's see if purple works better. Then I'm going to divide by this. So I'm going to go ahead and make the jump that dividing by this fraction is the same as multiplying by its reciprocal. So I'm going to put this up here and this down here.
Equations look so exciting.
It is. It's a very excited problem. Kind of like y'all. You're very excited. Some of you have problems. I wrote it like that because remember how the k plus 1 factorial and the k factorial cancels. K plus 1 factorial is k plus 1 times k factorial. I'll go ahead in this problem put that step in subsequent problems I won't. I'm going to go ahead and simplify this and write this as 2k plus 2 factorial. So that's k plus 1 times k factorial, and so is that one. So that allows me to cancel those k factorials, top and bottom. And now let's think of 2k plus 2 factorial is itself times integer reductions of it. So I can say that 2k plus 2 factorial looks like 2k plus 2 multiplied with 2k plus 1 multiplied with 2k. And then from here on out, all of these mimic 2k factorial. So that's this numerator. Then we have a couple of k plus 1s underneath it. And those canceled, so I just have 1 over 2k factorial here. So the 1 over 2k factorial cancels with the 2k factorial on top. And now we have to take the limit with what's left. So what's left is this product and that product. If you were to multiply them out, they'd both be k squareds. The coefficient of the k squared on top would be a 4. The coefficient of k squared on the bottom would be a 1. So do you agree that this limit is 4? So we're just looking here, that times that gives you a 4k squared plus lower power terms. That times that gives you a k squared plus lower power terms. So that limit is equal to 4. So that's bigger than 1. And our conclusion now is that this series diverges. Limit is bigger than 1. Okay? So let me show you where this doesn't work well, right? The things that we were using in our comparison tests earlier. Okay, so this series, k plus 1 divided by k squared plus, I don't know, 2k. This is a great candidate for a comparison test. It's a crappy candidate for the ratio test, and I'm going to show you why. This type of series is not a great candidate for a ratio test. Here's why. Let's just do it. Let's take the limit of the k plus first term and divide it by the k term. So let's see, to get the k plus first term, I put a k plus 1 here. So my numerator looks like k plus 1 plus 1. I'm going to go ahead and write that as k plus 2. Then I have a k plus 1 all squared plus 2 times k plus 1. Then I divide by that, but dividing by that is to multiply by the reciprocal. And not a dang thing cancels. I don't have a k plus 2 to cancel. This is nowhere near that. Nothing at all cancels because of the plus signs. But beyond that, can you tell me what the value of this limit is? You are assuming correctly. On top, if I were to multiply that out, I'd have a k cubed as the highest power of k. If I multiplied this out, I'd have a k squared, which would be eventually multiplied by that k. So I'd also have a k cubed, both of them with a coefficient of 1. So I get a limit of 1. This test is inconclusive. Okay. Instead, I'd compare it to that series, 1 over k. Do a limit comparison test with 1 over k, and I can show that that diverges. right? Instead, compared to k over k squared, which is a divergent p series. I'm going to do the limit comparison test, where I take the limit of my given series to my comparison series, and if I get a positive finite limit, the conclusion is they both do the same thing. The AK has a k plus 1 over k squared plus 2k. I'm going to divide it by that, so let's go ahead and flip and multiply. The top behaves like a k squared polynomial. The bottom is a k squared polynomial. So I have k squared over k squared, I get a positive limit of 1. Any positive finite limit means both series do the same. They both do the same thing. So I look up here, my comparison series is a divergent series, so that series diverges. Okay. That's also something that's easy to integrate, right? U is the denominator, du is nearly the numerator. So you're integrating 1 over u du, and that integral diverges. You're starting to see those things now? You're starting to see things that you can integrate? Because I know you're going to try the ratio test on everything, because every student loves the ratio test best. Because you get to do cool things like cancel. If you feel so forceful when you cancel things. And then I'm going to have students who tell me that I can cancel maybe this k with that k, and you can't. The plus sign keeps you from canceling. So don't be whipping out your bad algebra skills. Keep those hidden for a little bit longer. You can only cancel through a product. You guys doing okay in this old hot room? Why haven't you turned that heat off yet? I'm up here sweating. Sweating like a sumo wrestler up here. Hot. Put the number up. Come on. Let's see. All right, let me do one that you can do all the way through all by your lonesomes. These are all my comparison tests. That's no good. All right, let's try this one. Two k factorial divided by k raised to the k power. So k powers and factorials are clues that the ratio test is good. Let me get you to see if you can set it up and how far you can cancel. So I'm going to stand here and act like I'm doing something while you guys actually do the something. I'm putting the marker down. I'll walk around if you need me. Let me see, maybe this would be a good time to give away some test papers. That's some other people. Yeah. Yeah, that's the part I need to catch up on. Oh, goodness. About 2 steps in, it's a kind of a hard little limit there. You can jump in on this. plus 1 to the k and k to the k. Sorry? Let me do that part. All right, this is trickier than it looks. Such is life, right? Trickier than it looks. So the k plus first term looks like 2 times k plus 1 all factorial, k plus 1 factorial, no, sorry, k plus 1 raised to the k plus 1. Then I flip and multiply and put a k to the k and a 2k factorial. And so this is a 2k plus 2 factorial, which looks like 2k plus 2 times 2k plus 1 times 2k factorial. That's what that simplifies to. We'll leave that as k to the k. I'm going to rewrite this as k plus 1 to the k and k plus 1 to the 1. And then here's my 2k factorial. So cancel the 2k factorials. Okay, red went dry on me. It's easy to take the limit here, but this limit is hard. So I'm going to pull that particular limit out and do it separately. Remember that in calculus, if you've got the limit of a product, you can do it as the product of the limits. So I know here the limit of that, but I'm going to find out what the limit of that is. So let's pull this out to the side. So let's look at the limit as k goes to infinity of k to the k over k plus 1 to the k. Which I'm going to put together like this. Because when you look at it like that, this has the indeterminate form of 1 raised to the infinity power. How do we do limits like that? What? Use a logarithm. Gotta use a logarithm. So let's pretend that this is some number L and take the natural log of both sides. Because that logarithm lets me bring the k down in front. But now it has the form of infinity times the natural log of 1, which is infinity times 0. So what's next? Divide by the reciprocal. Divide by the reciprocal. 1 by k is equivalent to dividing by 1 over k. Then we can use L'Hopital's rule. So now I've got the natural log of 1, which is 0, and 1 over infinity, which is 0. I've got 0 over 0, so we can do L'Hopital's rule right there. So the derivative of the log of u is 1 over u times u prime. So 1 over u gives me k plus 1 over k. Then u prime is, by the quotient rule, the denominator times the derivative of the numerator, which is just 1, minus the numerator times the derivative of the denominator, that's also 1, over the denominator squared. Then the derivative down here is a negative 1 over k squared. So in the parentheses there, I lose the k's, and I have 1 over k plus 1 squared. Divide by that's going to put a k squared up here. All of that's equal to the natural log of L. I got all that. Clean that up enough for you. Knock off one of the k plus 1 squared terms. And what's left? Oops, no, that one went dry. Why don't I put the covers on these? Goes out with one of those. That goes out with one of those. And I'm left with the limit. K goes to infinity of k over, even the minus k, over k plus 1. So this limit over here is just a negative 1. So e to the negative 1 is L. So that came from here. Let me break this up. Right? I factor them separately.
Can we cancel the k plus 1?
Where?
If you pull out the 2 from the 2.
Oh, yeah, that would cancel here.
Yes.
So it's clear that this becomes infinite, right? Because there's only a numerator. This we said became e to the negative 1. So this limit is infinite. Well, where I come from, that's bigger than 1. What's the conclusion when the ratio test is bigger than 1? Diverges. A lot of work, but it diverges. Yes, sir.
Did we really need to do that second part? Did we just see that the limit as contiguous to infinity of 4k plus 2 infinity?
Right. Except, what if this had come out to be 0? Then we'd be in trouble. It can't come out to be 0 because we know it's going to be exponential, right? But then I think some of us need practice doing this anyway. Because if this were upside down, then that limit would have been 0 times e to the first. We'd have 0 limit, and we have a different conclusion. So I did it because I knew that you need to see it. That kind of thing shows up in the middle of problems a lot. Why don't you take a little break? I'll show you the root test, and then we'll start talking about alternating series. is it? This was the quotient rule. The derivative of log of u is 1 over u, so I just
Yes.
flipped it over, times u prime. So bottom times the derivative of the top, minus the top times the derivative of the bottom, which is just 1, over the bottom squared. So that's the 1 over u prime thing.
Oh, okay, okay.
That's the derivative of the logarithm that's on top.
So I have this like in my notes right here. Sorry. Well, it's this property, like the e to the -1. What changes it to be like e to the -2?
As soon as I start putting some other number here or here,
Okay.
right? So if I start putting other numbers in the
Is there
numerator.
a
and
rule for
denominator.
that, or you just have to?
I don't know the
figure it
general
out?
rule. Maybe there is one, but I don't know it off the top of my head to say
Okay.
that this happens all the time.
Okay, I just wanted to make sure.
Chris Beard's gone.
Gone. It's not official yet, so don't be quoting me on
A
that.
whole bunch of stuff just came out.
Did it?
I wish it would be April Fool's, but I don't think it is.
He did it. He did it. That was my call at the beginning of the class. He's not getting more money. We gave him sun, moon, and then some. He's going because he's going. It's okay. It's okay. We'll be all right. Sir. John? Oh, what happened? Our basketball coach is leaving us for Texas. You wouldn't do that, would you? You're not gonna transfer from Texas, are you?
I don't even know where Texas is.
It's in Austin.
Okay.
UT.
All right.
Somewhere in Texas.
We don't call it UT, we call it TU. Can you imagine having a wardrobe with orange? Ew. Is that color orange? Like baby cuckoo orange?
It's like a burnt orange.
It's baby cuckoo.
I know this costs a lot.
let's do another 50 minutes. How about it? You got another 50 minutes in you? Feeling good? All right, last bit in this section is something called the K through test. And it's a cousin of the ratio test. So if my subscript is a K, it's called a K through test. If my subscript is an N, then it's the N through test. But it says, grab the nth term or the kth term. If it is a power term, the kth power, just take the kth root of it. And then take the limit of what's left. If your limit is smaller than 1, then your series converges. If your limit is bigger than 1, your series diverges. If your limit is equal to 1, this test is inconclusive. So again, we're dealing with a positive term series. We take the limit as k goes to infinity of the kth root of ak. So remember, a kth root is a 1 over k power. Suppose. And suppose you get some number L. Same 3 conclusions as with the ratio test. If L is smaller than 1, the series is convergent. If L is bigger than 1, the series is divergent. If L is equal to 1, use a different test. But this test is very, very limited. What you need in order to use this test is all of the terms in your series have k powers. If any one of the terms doesn't have a k power, this is harder to use than the ratio test. But if every single term is raised to the k power, then this is a quickie. If there's any addition or subtraction of terms, if I have a k to the k plus 2, I'm not going to use it. I want to be able to have cancellation enough so that I can take this limit easily. We need this step to go easily. And the only way for that to happen is if everything in here is raised to the k power so that the kth root would cancel it. So an example. I want to test the series. K is equal to 2 to infinity of 1 over the natural log of k to the kth power. So it doesn't matter if that 1's up there, because 1 to the any power is 1, right? 1 to any power is 1, so we're okay there. I can also think of this as being the same as this. So there I have everything raised to the kth power. And so I do the kth root test. And it almost takes longer to write than to do. I'm going to take the limit as k goes to infinity of the kth root of that general term. So I'm taking the limit as k goes to infinity of 1 over the natural log of k to the kth power to the kth root. So we want it to be this obvious. We want to be able to just knock that power off and look at the limit of the stuff that's inside. K power, K root. Undo each other, we're left with the limit of 1 over the natural log of K. The only activity belonging to K is on the bottom, so that limit goes to 0. If the limit is smaller than 1, our series converges. Now, we had an example from earlier. We did something like K divided by 2 to the K. Then I wouldn't use the K root test. I would use the ratio test. So note the series K divided by 2 to the K is not a good candidate for the K root test because my numerator doesn't have a K power. Taking the limit of K to the 1 over K is tricky. So just use the ratio test. You want everything to have a Kth power. Yes, sir.
Is there an example where we're going to get a series that works with the root test but not with the ratio test?
No, because I bet I could do the ratio test on this one and not have much difficulty. But the root test is so quick on it. So I don't think so, but I can find plenty that use the ratio test easily and the root test hard. So how about something like this? So do it in your head. What's your conclusion? The limit's 3. 3 is bigger than 1. Series diverges, right? It's that fast. You take the kth root, means we just ignore that kth power out there, take the limit of the stuff inside, see what happens. In this case, it's going to give us a 3. That's bigger than 1. We're done. Okay? I write it down because that's what I'm paid to do. Okay.
What if the power is not K, it's like 2K or 2K?
Okay, if it was 2K, let's just do it. This is 2K, we're good. Because remember, a kth power, or kth root is a 1 over K power. So you have this stuff over here to the 2K, then raised to the 1 over K power. And what is it that you do with exponents? You multiply them, right? So the only difference is, in this step, I would have the limit as K goes to infinity of 3K minus 1 over K plus 4 squared. So it does just cancel the K. And then I get the 3 in here, square it, gives us 9. Same conclusions. Bigger than 1, it diverges. So it can be, some multiple of k. K plus 1 is really not good. If we're a k plus 1 power, I would do a ratio test. Or k power. I can do k plus 1. I can write it as itself times it to the 1. That's not so bad, but it's easier to do the root test if your power is some k.
Factorial?
K factorial is bad. K factorial, I do the, I don't know what the k through to k factorial is. Right? Do I have to take a limit of something like this? That's, oh gosh, that's hard. That's one of my terms in my series. I wouldn't even know what to do. Right? That's just one of the terms. So I want k powers. I don't want k factorial powers. I don't want k plus 3 powers. I want k powers. Yes, sir.
What would k to the k factorial look like?
Something grows pretty dang quick. So there's the root test. I say little about it because it's not one I use often unless the power is k. I wouldn't use it on something like this. Even though it would apply. Because it's easy to look at that as a geometric series. Right? Instead of knowing that that's a geometric series, I can even get the sum of it. Doing the kth root, all I could say is it converges. Right? So kth root test would work. I get the kth root of that is 2/3. The limit of that then is still 2/3. Smaller than 1, it converges. But then I want to know what it converges to. So then I have to identify it as a geometric series. Okay? What about this series? Does the kth root test tell you about that one? You just get a 1 as your limit, so what does the kth root test say? I don't know. That's all it says. I don't know. Limit's 1, right? Kth root of that gives us that. Limit of that is a 1. So the kth root test is inconclusive. So what would you use? That's right, I'd use the test for divergence. I've done this so many times, I know that the limit of the general term is not 0. The limit of the general term in this example is e. So I'd use the test for divergence. So just stay on your toes. Remember the things you know and don't know. I know something that looks like that is some version of E. If I don't know which version of E, I go through all the steps with the logarithm and compute the limit that way, but I know the limit's not 0. So there's no reason to do a kth root test on that, even though I've got this big old K hanging out here. If the test is inconclusive, try something else. Okay? Okay, so this is where we stop looking at series with positive terms only. Now we're going to look at series whose terms might alternate in sign or might pass through a bunch of negative signs, a bunch of positives, a bunch of negatives, a bunch of positives, that the terms in the series are not positive terms. If they're positive term series, we've got the test for divergence, we've got geometric p-series integral test, the two comparison test, ratio test, root test. It's important to know what works when. I have a handout on Blackboard that's a comprehensive outline of all the tests we have so far, with some examples of problems that work well with that particular test. So I urge you to go and run that off and use it next to you as kind of a little cue card when you're doing your homework, so that it gets embedded in your head. So look at that, carry it with you everywhere you go. Because now we're going to add some stuff to it. So we're in section 8.6 now. There are two main topics in section 8.6. The first one deals with an alternating series, and then the second topic deals with series that are considered to be absolutely convergent. So we've got alternating series in here. And then we have absolute convergence versus conditional convergence. Whew. Alternating series. Has the form -1 to the n times some positive term here. Oops, I better use a k if I'm using a k. So k might go from 1 to infinity, or I might have first term positive, in which case this would be a -1 to the k plus 1. Depending on where I start the counter and what the exponent is, the first one I've written has the first term is negative. So it looks like when k is 1, I get a -1 times a1. When k is 2, I have a positive 1 times a2. And then minus a3 plus a4. This one has the first term being positive. So a1 minus a2 plus a3 minus a4, and so on. So when you look at the picture of these, you've got terms that take on values here, then here, then here, then here, then here, then here. You have some of them up here, some of them down there. We still kind of need that they eventually go to 0. That's what an alternating series looks like. To test whether an alternating series converges, we just look at the non-alternating part. And we need it to do two things. We need it to decrease, and we need it to go to 0. Those two things. Alternating series test has 2 steps. Step 1, does this term here without the alternating part go to 0, and does it decrease? It needs to be decreasing and limit to 0. So the alternating series test. so-called alternating series test. Applies to either one of these two things, and you need two things. If, step one, the limit of the AK terms is 0, and that's infinity. Number two, the AKs are decreasing. So one way of saying that is that AK plus 1 has to be smaller than AK. Then the alternating series of either form converges. The non-alternating term has to go to 0, and it has to form a decreasing sequence of numbers. So if you're from Texas, you like this test. It has 2 steps. This series whether it's K or K plus 1. I put K plus 1 because I want my first term to be positive. This series looks like 1 over K minus 1 over K squared plus 1 over K cubed minus 1 over K to the 4th. So if I isolate the alternating part, then my AK term is just 1 over K. This is called the alternating harmonic series. Whose cousin is this P series, which was the harmonic series. Without the alternating part, as a positive term series, this is a divergent P series, right? 1 over K to the power of 1 is a divergent P series. As an alternating series, it converges. Show you that it converges by doing the 2 steps. So using the alternating series test, I have my step 1. I take the limit as K goes to infinity of 1 over K, and that's obviously 0. So that part checks off. I check the decreasing part. I know that K plus 1 is bigger than K, so 1 over K plus 1 is smaller than 1 over K, which means it's decreasing. Boom. By the alternating series test, this feller converges.
Limit of AK goes to 0, isn't it always going to be decreasing?
I could probably find some that isn't. That is kind of a formality, but I could probably find something that isn't. It does seem redundant. In fact, any alternating P series converges. Any alternating P series converges. Put a power up here. Put a 1, put a 2, put a 1/2. That power here is going to still have a limit to 0. I'm still going to be able to do this step. Any alternating P series converges. One over K to a P is going to go to 0. And it's going to be decreasing because I can just do the same steps, but just throw a power of P on there.
Even if P is less than 1.
Even if P is less than 1. If this was a half power right here, this is a half power right here, that still goes to 0. If this is true, then taking the square root of both sides keeps them in the same order. Flipping them keeps them in the same order. No matter the size of P. Which gives us this concept. That particular alternating series will converge only if it alternates. But if I take the absolute value of it and get only positive terms, it's going to diverge for particular sizes of P. That's what we mean by conditional convergence versus absolute convergence. If it converges in absolute value without the alternating part, if we made all the signs plus signs, then it's absolutely convergent. If we need the alternating to make it converge, then it's only conditionally convergent. Okay, but I'll get to that in a bit. Let's look at some more alternating series. Now notice that our telescoping series are not alternating series because we end up getting just 2 terms, the first one and the last one. So you don't need to use an alternating series test on the things that telescope. There's an alternating series. Is equal to 1 to infinity, negative 1 to the k, divided by, I don't know, it's kind of redundant. Let's see what I got here. My notes. Oh well, we'll just do this one. So here's the giveaway that it's an alternating series. The non-alternating part is just 1 over k plus 2 to the k. Or 2 square root of k. 2 to the k. So alternating series test. Limits k goes to infinity. That has only k's in the bottom. Is it decreasing? Yeah, I make this bigger. I make that bigger. Sum then is bigger. That's a bigger number. And that divided into 1 makes that fraction smaller. So by the alternating series test, the series converges. Change the example to this. Slip a K in there, and my alternating series diverges. Right? Slip a K in there, and I have this. And I'm done right here. What's that limit? 1. Divergence. Okay, so you don't even need to do part 2. All right, so next part. Oh, I got to tell you this part. This part's important. In an alternating series, we have a way of approximating what the sum of the alternating series is if it's convergent. If we have a convergent alternating series, we can approximate the sum of that infinite series to whatever level accuracy we want with a formula. Somebody smarter than me came up with the formula. Hard to believe, right? If the series is an alternating divergent series, we can make it add to almost anything just by switching terms around. So you've got to be careful of approximating the value of an alternating series. You got to make sure it converges first. And so let me find my formula in my messed up notes here. Okay. So here's a big theorem for people who are into math. Suppose either alternating series, the one with the positive first term or the negative first term, is a convergent alternating series. Then, if I use S as the sum of the infinite series, and S with the n subscript as the sum of n terms of the series, then I can make the sum of the infinite series as close to the sum of the n terms as I want, because I know that this is always going to be smaller than whatever the term is that I truncate, the next one. So Sn represents A1 plus A2 plus A3 on out to An, and An plus 1 is the next term. So S is the actual sum of the infinite series, and Sn is equal to the sum of n terms. Sum of n terms of the alternating series, so it includes the alternating in sign. So it's either A1 minus A2 plus A3 out to An, or the other way, minus A1 plus A2 minus A3 out to An. It does include the alternating sign. And this is the term that was left off when we truncated the sum at An. And here's an example. example fast. The series 1 over 1 factorial minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial, and so on, can be written as the sum from k is equal to 1 to infinity of -1 to the k plus 1. And now I've got odd factorials down there. I can write odd factorials as 2k plus 1 factorial. Right? If k is 1, this gives me 3 factorial. Uh-oh, I better start with -1. If k is 1, this gives me 1 factorial. If k is 2, it gives me 3 factorial. Yeah, let's do it with the -1. That series is convergent as an alternating series. Because the limit as k goes to infinity of 1 over 2k minus 1 factorial is 0. K is on the bottom. And it's decreasing because 1 over 2 times k plus 1 minus 1 factorial has a huge factorial denominator compared to this one. So it's decreasing. If I want to approximate the sum of this series to a certain number of decimal places, I just start looking at what these values are and see how small they are. For instance, suppose I want to approximate, some of the series accurate to 1, 2, 3, 4, 5 decimal places. So if I round up, that hits, let's say accurate to 5 decimal places. Then I get out my calculator and I start adding them, and I stop when 5 decimal places isn't affected. So I'm going to figure out how many terms that is. So how many terms do I need to add to get that? So that S minus Sn is smaller than, let's see, 1, 2, 3, 4, 5, and maybe at worst, the 6th place would be a 5, so it would round up. So I'm looking for what term number has that going on with it. So this is A1, this is A2, this is A3, that's A4. And A5 would be 1 over 9 factorial. A6 would be 1 over 11 factorial, and so on. So I get out my calculator and I start punching numbers. And I find that 1 over 9 factorial looks like some number 0.1, 2, 3, 4, 5, and then a 3 right here. Where 1 over 4 factorial has things in these decimal places. So that means if I just add these up right here, I'm within the required tolerance. And what you're going to find out at the end of this chapter is that this series is exactly equal to the value of the sine of 1 radian. And so this was S5. And so if I add up 1 over 1 factorial minus 1 over 3 factorial plus 1 over 4 factorial, 5 factorial, minus 1 over 7 factorial, I get something like 84147. And if you try that on your calculator, put your calculator in radians and calculate the sine of 1 radian, it's going to be pretty dang close to that. At least it's going to be that to the 5th decimal place. If your calculator's in radians. Yeah,
Checks out.
checks out. I'm not lying to you today.
So what's S5?
I'm sorry?
What is S5?
S5 is the 5th term, 1 over 9 factorial.
Oh,
Right? This is S1, A1, A2, A3, A4, and that would be S4. Yes.
If you flip the signs, would it become a cosine?
No, cosine's an even function. So cosine will look like 2 factorial, 4 factorial, 6 factorial. Cosine's an even function. Very cool. Yes, sir.
Do you still get sine if you flip the sign?
Say it again?
If you flip the plus and minuses, do you still get sine of 1?
No, you get minus the sine of 1, right? If I did minus, plus, you get minus the sine of 1. Yes, sir.
So if the series wasn't k plus 1, it was just k, it would be negative sine?
Correct, of 1.
Right.
Yes, sir.
How do you get a tangent?
Sine of a cosine.
Okay.
But you can't do term-by-term division, so you have an infinite series over an infinite series. We are going to build series for tangent. We're going to build series for transcendental functions. At the end of this chapter, right, we're going to make functions of x, right? Functions of x that have derivatives, that have integrals. And sometimes derivatives and integrals are hard to compute, but if we can write a function of x as a polynomial, polynomials are easy to take derivatives and integrals of. And that's what we're going to do at the end of this chapter. So we got to get there first. So I want to talk about absolute convergence versus conditional convergence. All the examples that I did today with alternating series need the alternating part in order to converge. The alternating P series needs to alternate in order for that to converge for P smaller than or equal to 1. The 1 over K plus the square root of K with the alternating part, got to have the alternating part. Those are all examples of series that are conditionally convergent. A series is said to be absolutely convergent if it converges an absolute value. Whether it has an alternating part or negative terms. Series is said to be absolutely convergent if it converges an absolute value. If it doesn't converge an absolute value, but it converges with, for instance, the alternating part, then it's said to be conditionally convergent. If this does not converge, but this does converge, then the series is said to be conditionally convergent. So the prime example of a conditionally convergent was, say, the alternating harmonic series. Is conditionally convergent. Because when I take the absolute value of that, that's a divergent P series. And we showed earlier with an example that this satisfied the two steps of the alternating series test. So that's an example of something that is conditionally convergent. This is an example of something that is absolutely convergent. Sign of K has some values that are positive. It has some values that are negative, then it goes positive again, but it doesn't alternate. It has a bunch of positive terms, and a bunch of negative terms, and a bunch of positive terms. K squared is always positive. So it changes sign, but not in an alternating way. But I showed you earlier with a comparison test that when I put that in absolute value, we only need the absolute value on top because K squared is already positive. That when I write that as the absolute value of my kth term, I can compare it to 1 over K squared. Where 1 over K squared is a convergent P series, and smaller than convergent is convergent.
I didn't get that. Could you try again?
Smaller than convergent is convergent series.
I found this on the web.
Thank you. Okay, so that's an example of an absolutely convergent series. If something's absolutely convergent, that means the strongest sense of convergence. That means it's automatically conditionally convergent. But if something's conditionally convergent, that doesn't necessarily mean it's absolutely convergent. So we'll always check for absolute convergence first. What happens if all the negative signs are gone? Will it converge? If it does, you're done. You say it's absolutely convergent. If it doesn't, you try something else. Right now, the only other thing else we have is the alternating series test. But we also have the ratio test. If you do the ratio test and put absolute value around your limit, If that ratio test converges according to the size of L, then your series is absolutely convergent. And you don't have to test the alternating series. Okay, so we have a general ratio test. It looks just like the ratio test, but it has absolute value bars here. Blow off the negative junk. If that number is equal to L, it converges for L smaller than 1, and you say it's absolutely convergent for L smaller than 1. It diverges for L bigger than 1, so then you check for conditional convergence with the alternating series test. And it's inconclusive if L is equal to 1. So you just do this instead. Okay, so we'll do some stuff on that. All of the positive term series that we tested with the ratio test and got convergent, you can automatically say they're absolutely convergent. If a positive term series converges, it absolutely converges because it's positive. Okay? All right, we'll try that same deal with the general ratio root test. If I put absolute value bars and then take the kth root, I get the same conclusions, absolute convergent or not. So we'll do some examples where we have to check for conditional convergence. Like I said, all the examples we did today were all conditionally convergent. If you did them in absolute value, they're not going to converge. All right, I'll put some web work up there for you. And you guys go out and find us a new basketball coach who can get us to the tournament.
Isn't there a alternating series that estimates pi?
Yes?
Do you know what
I don't know off the top of my head.
it is? I was trying to.
Yes, I've got your papers up here. Come back. Here, they're in here.
Thanks.
Thank you.
For the sine series thingy, is the numerator the equal to the degree put in the sine function?
Ooh, baby doll. Is the sign the numerator?
Yeah, the numerator. Because you said it was sine
Kinda,
1 and 1 was on
kinda.
top.
You're gonna see that in when we do power series.
So if we put like 30 over all that stuff.
Not quite.
It wouldn't be equal
Not
to sine
quite.
30?
There are, if you do this for sine of x, there's powers of x in the numerator. So it wouldn't quite be the 30.
When you started writing down like the factorial plus minus all one after the other,
Uh-huh.